Hello. Today I got that somehow. We are doing rotational motion and uniform circular motion with Beyblades. Um, let's see if I can get the camera to be able to see. So, hold on, let me do that. So, it moving around the stadium like that is able to stay stable because it's spinning. It creates a gyroscopic force that just keeps it upright. Whenever you try and push it, it resists it because it wants to stay stable. The further out from the center of the Beyblade it is, technically speaking, the faster it's spinning through tangential velocity. The closer it is to the middle, the slower it's spinning, even though their angular rotation velocity is the same, because they're all traveling the same amount of angles in the same time frame. The distance traveled by the outer points or the inner points is different, because it's farther away from the center. When two or more of these interact, they change the way they move around in the stadium. And certain parts, like, say, a Beyblade that has a sharp pointed tip versus a flat tip, will move around differently. The flat pointed tip will act more aggressively in the stadium because it has to cover a wider surface area to stay stable. Whereas with this, it wants to stay more stable because it has less surface area to cover. So, now, it might be a bit hard to hear me because of how loud these can be, but the one with the pointed tip, generally speaking, wants to stay spinning longer than the one with the flat tip because, well, it has less surface area, therefore less friction. And when designing a Beyblade that is made to spin longer, you want to have a Beyblade that has the least amount of friction possible. So, the rounder, the better. The less contact with the stadium, the better. Because if it has a lot more jagged edges, like this one, it will want to catch on the air more, and that'll cause air resistance. Whereas if it's rounder, like this one, it won't want to do that as much because the air will just bounce off instead of being caught in the blades. So whenever they're in the stadium, because they're being pushed by friction and just general forces whenever they're spinning, they tend to orbit around the stadium in a circle. In this case, not so much because this is more of like an oval-shaped stadium. And they also have gear teeth, so whenever they're spinning, they'll be propelled into the center and knock them out here. Not every stadium is like this, but that's besides the point. Oh my gosh. Let's see. And because they rotate around the center, you can assume that the center of the stadium is kind of like an axis. The stadium is shaped like a bowl, so they're more naturally inclined to stay at the center. But because of a force called centripetal force, they're more so forced around the outside. Similar to how if I were to take this mouse, for instance. I'm not going to swing around this part, but I'll swing around this part. If I hold the cord like so, the outer edge of the USB will want to orbit around, but it'll still be held in place. Because if I let go, it flies off. And that is tangential velocity, whereas when it's staying in place, it's more so rotational. And you can increase the diameter. It's still rotating the same amount. It's covering the same amount of degrees in the same amount of time. But the distance it has to travel is farther, because the radius increases, whereas if I shorten the radius, it's still the same amount of angles or radians, degrees, whatever you want to call it, but it's traveling a shorter distance because the radius is shorter. Thanks for watching, I guess. I don't really know how to end this. Yippee.